The 6-inch separation distance or 90-degree crossing angle is specified to minimize electromagnetic interference or EMI between the power cables and control wires. EMI occurs when the alternating current in the power cables induces a voltage in nearby conductors, such as the control wires. This voltage can interfere with the control signals, causing errors or malfunctions. The triangular and square bundling configurations are designed to minimize EMI by reducing the magnetic flux leakage from the power cables. The shape of the bundle creates a closed magnetic loop that contains the flux within the bundle, preventing it from reaching the control wires. For triangular bundling for 3-wire cables, the 3 wires form a triangle, with the wires spaced equidistantly. The closed magnetic loop confines the flux to the triangle, minimizing leakage. This configuration is commonly used for 3-phase power cables. For square bundling for 4-wire cables, the 4 wires form a square, with the wires spaced equidistantly. The closed magnetic loop again contains the flux, minimizing leakage. This configuration is commonly used for 4-wire power cables, such as 3-phase with neutral. Bundling the power cables creates a more compact and organized arrangement in the cable tray. It also helps to reduce the overall magnetic field produced by the cables, as the flux is concentrated within the bundle. This further minimizes the potential for EMI. The specific separation distance, crossing angle, and cable bundling configurations prescribed in the spec are designed to mitigate EMI and ensure reliable operation of the control system. By following these guidelines, engineers can minimize the risk of interference and maintain the integrity of both the power supply and the control signals. Electrical interference, also known as electromagnetic interference or EMI, is a disturbance caused by electromagnetic radiation emitted from various sources. This interference can disrupt the performance of electronic devices and systems. Sources of electrical interference include power lines, radio transmitters, industrial equipment, and even natural phenomena like lightning. The effects of EMI can range from minor annoyances, such as static on a radio, to serious malfunctions in critical systems like aircraft, avionics, or medical equipment. EMI can manifest in several forms, including conducted interference, which travels through wires and cables, and radiated interference, which propagates through the air as electromagnetic waves. To mitigate the effects of EMI, various techniques are employed, such as shielding, filtering, and grounding. Shielding involves enclosing sensitive electronic components and conductive materials to block electromagnetic radiation. Filtering uses electronic circuits to attenuate unwanted frequencies, while grounding provides a low-impedance path for stray currents to return to the source. Regulatory bodies, such as the Federal Communications Commission or FCC in the United States and the European Union, set standards for electromagnetic compatibility or EMC, which require electronic devices to meet certain limits on EMI emissions and susceptibility. These standards aim to ensure that electronic devices can coexist without causing harmful interference to each other. Electromagnetic compatibility is achieved through careful design and testing of electronic devices. This includes selecting appropriate components, designing circuit boards with low impedance ground planes, and using shielded cables and connectors. Testing involves measuring the emissions from a device to ensure they are within the limits specified in the EMC standards. It also involves subjecting the device to electromagnetic fields to assess its susceptibility to interference. In addition to technical measures, proper installation practices can also help to minimize EMI. This includes separating power cables from signal cables, using shielded cables for sensitive signals, and grounding equipment properly. Regular maintenance and inspection of electrical systems can also help to identify and address potential sources of EMI. In summary, electrical interference is a pervasive phenomenon that can affect the performance of electronic devices and systems. By understanding the sources and effects of EMI and implementing appropriate mitigation techniques, it is possible to minimize its impact and ensure reliable operation of electronic equipment. Cable trays are structural systems used to support a router, electrical cables, and wiring. They are commonly used in commercial, industrial, and utility applications to manage large quantities of cables in an organized and safe manner. Cable trays offer several advantages over traditional conduit systems, including greater flexibility, easier installation, and better accessibility for maintenance and upgrades. Cable trays come in various types and materials to suit different applications and environments. The main types of cable trays include ladder trays, ventilated trays, solid bottom trays, and wire mesh trays. Ladder trays consist of two longitudinal side rails connected by rungs or cross members, providing excellent support and ventilation for heavy cables. Ventilated trays have perforated bottoms to allow for airflow and prevent heat buildup. Solid bottom trays provide maximum protection for sensitive cables but may require additional ventilation. Wire mesh trays are made of welded wire mesh and are lightweight and easy to install. Cable trays are typically made of steel, aluminum, or fiberglass. Steel cable trays are the most common due to their strength and durability. Aluminum cable trays are light and corrosion resistant, making them suitable for outdoor or corrosive environments. Fiberglass cable trays are non-conductive and resistant to chemicals, making them ideal for use in hazardous locations. Cable trays are designed to support the weight of the cables and withstand various environmental conditions such as temperature variations, humidity, and exposure to chemicals. They are typically installed overhead, but can also be mounted on walls or under floors. Cable trays are available in various widths and depths to accommodate different cable sizes and quantities. The installation of cable trays involves several steps, including planning the route, selecting the appropriate type and size of tray, installing support brackets, and laying the cables. It is important to follow the manufacturer's instructions and local electrical codes to ensure safe and compliant installation. Proper grounding of cable trays is essential to prevent electrical hazards and minimize electromagnetic interference. Cable trays should be grounded to a common grounding point using appropriate grounding conductors and connectors. Regular inspection and maintenance of cable trays are necessary to ensure their continued performance and safety. This includes checking for corrosion, loose connections, and damaged cables. Any issue should be addressed promptly to prevent potential problems. In summary, cable trays are an effective solution for managing and supporting electrical cables in a wide range of applications. By selecting the appropriate type of tray, following proper installation practices, and performing regular maintenance, it is possible to ensure a safe, organized, and reliable cable management system. Three-phase power is a method of electrical power distribution that uses three alternating current or AC voltages that are 120 electrical degrees apart. The system is widely used for industrial and commercial applications due to its efficiency, reliability, and ability to deliver high power levels. In a three-phase system, the three AC voltages are generated by a synchronous generator with three sets of windings, each set displaced by 120 degrees. These voltages are typically referred to as phase A, phase B, and phase C. The phase voltages are sinusoidal waveforms that vary with time, but the phase relationship remains constant. There are two main configurations for connecting the three-phase voltages: a Y or Y connection and a delta or triangle connection. In a Y connection, one end of each winding is connected to a common point, called the neutral point, while the other end is connected to a phase conductor. The voltage between each phase conductor and the neutral point is called the phase voltage, while the voltage between any two phase conductors is called the line-to-line voltage. In a delta connection, the three windings are connected in a closed loop, forming a triangle. The voltage between any two phase conductors is called the line voltage, and it is equal to the phase voltage. Three-phase power offers several advantages over single-phase power, including higher power capacity, smoother power delivery, and greater efficiency. Three-phase motors are smaller and lighter than single-phase motors of the same horsepower rating, and they also have better starting torque characteristics. Three-phase power is used to power a wide range of equipment and machinery in industrial and commercial settings, including motors, pumps, compressors, lighting systems, and electronic devices. It is also used for long-distance power transmission, as it reduces the amount of current required to deliver a given amount of power, which minimizes transmission losses. To ensure safe and reliable operation of three-phase power systems, it is important to follow proper installation and maintenance practices. This includes using appropriately sized conductors, protecting circuits with fuses or circuit breakers, and grounding equipment properly. Regular inspection and testing of three-phase power systems are also essential to identify and address any potential problems. In summary, three-phase power is a versatile and efficient method of electrical power distribution that is widely used in industrial and commercial applications. Its advantages over single-phase power make it the preferred choice for powering high-power equipment and machinery. Electromagnetic interference, or EMI, is a disturbance that affects an electrical circuit due to either electromagnetic induction or electromagnetic radiation emitted from an external source. The disturbance may interrupt, obstruct, or otherwise degrade or limit the effective performance of the circuit. EMI can be generated by a variety of sources, both natural and man-made. Natural sources of EMI include lightning, solar flares, and atmospheric noise. Man-made sources of EMI include radio transmitters, television transmitters, mobile phones, industrial equipment, and electronic devices. EMI can be classified into two main categories: conducted EMI and radiated EMI. Conducted EMI is interference that is transmitted through wires or cables. Radiated EMI is interference that is transmitted through the air as electromagnetic waves. EMI can affect electronic devices in various ways. It can cause malfunctions, errors, data loss, and reduce performance. In some cases, EMI can even damage electronic equipment. To mitigate the effects of EMI, various techniques are employed. These techniques include shielding, filtering, grounding, and proper cable routing. Shielding involves enclosing electronic components and conductive materials to block electromagnetic radiation. Filtering uses electronic circuits to attenuate unwanted frequencies. Grounding provides a low-impedance path for stray currents to return to the source. Proper cable routing involves separating power cables from signal cables and using shielded cables for sensitive signals. Regulatory bodies, such as the Federal Communications Commission or FCC in the United States, set standards for electromagnetic compatibility or EMC, which require electronic devices to meet certain limits on EMI emissions and susceptibility. These standards aim to ensure that electronic devices can coexist without causing harmful interference to each other. Electromagnetic compatibility is achieved through careful design and testing of electronic devices. This includes selecting appropriate components, designing circuit boards with low-impedance ground planes, and using shielded cables and connectors. Testing involves measuring the emissions from a device to ensure they are within the limits specified in the EMC standards. It also involves subjecting the device to electromagnetic fields to assess its susceptibility to interference. In addition to technical measures, proper installation practices can also help to minimize EMI. This includes separating power cables from signal cables, using shielded cables for sensitive signals, and grounding equipment properly. Regular maintenance and inspection of electrical systems can also help to identify and address potential sources of EMI. In summary, electromagnetic interference is a pervasive phenomenon that can affect the performance of electronic devices and systems. By understanding the sources and effects of EMI and implementing appropriate mitigation techniques, it is possible to minimize its impact and ensure reliable operation of electronic equipment. Grounding is a critical aspect of electrical safety and is essential for preventing electric shock, fire hazards, and equipment damage. Grounding provides a low-impedance path for fault currents to flow back to the source, allowing protective devices, such as circuit breakers and fuses, to quickly interrupt the circuit and prevent further damage. There are two main types of grounding: system grounding and equipment grounding. System grounding involves connecting the neutral point of a power system to earth. This helps to stabilize the voltage and prevent overvoltages during fault conditions. Equipment grounding involves connecting the non-current carrying metal parts of electrical equipment to earth. This provides a path for fault currents to flow back to the source in the event of an insulation failure. The National Electrical Code, or NEC, provides detailed requirements for grounding electrical systems and equipment. These requirements are designed to ensure that grounding systems are installed and maintained properly to provide maximum safety. Grounding conductors must be sized according to the size of the circuit conductors and must be made of copper or other approved materials. Grounding electrodes, such as ground rods or ground plates, must be installed in contact with the earth to provide a low impedance connection. Grounding connections must be made using approved connectors and methods to ensure reliable and corrosion-resistant connections. Regular inspection and testing of grounding systems are essential to ensure their continued performance and safety. This includes checking for loose connections, corrosion, and damaged conductors. Ground resistance measurements should be taken periodically to verify that the grounding system is providing a low impedance path to earth. In addition to safety, grounding also helps to reduce electromagnetic interference, or EMI. Grounding provides a path for stray currents to flow back to the source, which minimizes the amount of electromagnetic radiation emitted by electrical equipment. Proper grounding is essential for sensitive electronic equipment, such as computers and medical devices, to prevent malfunctions and data loss. In summary, grounding is a critical aspect of electrical safety and is essential for preventing electric shock, fire hazards, and equipment damage. By following the requirements of the National Electrical Code and implementing proper grounding practices, it is possible to ensure a safe and reliable electrical system. A magnetic field is a region around a magnet or a current-carrying wire where magnetic forces are exerted. Magnetic fields are created by moving electric charges, such as electrons flowing through a wire. The strength of a magnetic field is measured in Teslas or T. Magnetic fields have a direction, which is defined as the direction that a north magnetic pole would move if placed in the field. Magnetic fields are represented by magnetic field lines, which are imaginary lines that show the direction and strength of the magnetic field. The closer the field lines are together, the stronger the magnetic field. Magnetic fields can be produced by permanent magnets, which are materials that have a permanent magnetic field, or by electromagnets, which are devices that create a magnetic field when an electric current is passed through them. Magnetic fields are used in a wide variety of applications, including electric motors, generators, transformers, and magnetic storage devices. Magnetic fields are also used in medical imaging techniques, such as magnetic resonance imaging or MRI. The Earth has its own magnetic field, which is generated by the movement of molten iron in the Earth's core. The Earth's magnetic field protects us from harmful solar radiation and is also used for navigation. Magnetic fields can interact with each other, either attracting or repelling each other. Like poles repel each other, while unlike poles attract each other. The force between two magnetic poles is proportional to the product of their pole strengths and inversely proportional to the square of the distance between them. Magnetic fields can also interact with electric fields. A changing magnetic field can induce an electric field, and a changing electric field can induce a magnetic field. This relationship is described by Maxwell's equations, which are a set of fundamental equations in electromagnetism. In summary, a magnetic field is a region around a magnet or a current-carrying wire where magnetic forces are exerted. Magnetic fields are created by moving electric charges and are used in a wide variety of applications. The NEC Table 310.15b3 details adjustment factors for ambient temperature. NEC Table 310.15b3 details adjustment factors for more than 3 current-carrying conductors in a raceway or cable. The NEC Table 310.16 specifies the allowable ampacities of insulated conductors rated up to and including 2000 volts, 60 degrees Celsius through 90 degrees Celsius, not more than 3 current-carrying conductors in raceway or cable or earth directly buried, based on ambient temperature of 30 degrees Celsius. The NEC Table 310.17 specifies the allowable ampacities of single insulated conductors rated up to and including 2000 volts in free air, based on ambient temperature of 30 degrees Celsius. The NEC Table 310.21 details adjustment factors for conductor temperature rating. The NEC Table 250.122 specifies minimum size equipment grounding conductors for grounding raceway and equipment. NEC Section 300.3b requires all conductors of the circuit, including the equipment grounding conductor, to be installed in the same raceway or cable. Article 250 of the NEC covers the general requirements for grounding and bonding. The NEC section 310.15 covers the general requirements for conductors for general wiring.